Quaternions were introduced by Hamilton in 1843. That's the same Hamilton as in Hamilton's principal fame. And Hamilton was inspired by the works of Euler and Rodriguez, who had published his rotation theory just a few years before this. He knew that complex numbers could be interpreted as points on a plane, and the multiplication of complex numbers as the rotation of vectors. And he was looking to extend this to rotations in 3 dimensions by extending complex number theory into 3, and ultimately it turned out 4 dimensions when he realized that the 3 dimensions were not enough to handle 3D rotations. And for some of you who might be confused by what I'm saying, let's embark on a quick digression just to talk about complex analysis and how these represent rotations. To some of you, I recognize that this might be review, but just bear with me. Okay, so a digression into complex analysis. Complex analysis, by the way, was ultimately formalized by Cauchy in 1820. If we consider the complex plane, and let's draw the unit circle on that plane, we of course have a real axis and imaginary axis. Now, if I consider a point on that plane, I can draw a vector from the origin to that point, and we can represent that point as a plus bi, where a and b are both scalars, and I is known to be the square root of -1. We can similarly represent this vector in polar coordinates by describing it as some radius r and an angle from the real axis, which we'll call θ1. And then by using Euler's formula, we can write this as r e to the I θ1. I could draw a second vector on the unit circle. This vector we will assume is an angle θ2 from the real axis. And of course, we can describe this vector as e to the I θ2, since the radius is 1. Now, if I multiply these two vectors, or these two numbers together, I get r e to the I θ1 times e to the I θ2. And we know the result of this. This is equal to r e to the I θ1 plus θ2. And if I were to draw this vector, r e I to the θ1 plus θ2, it would look something like this. And this has had the effect of taking this vector r and rotating it to this new position, which is at an angle of an additional θ2 from the real axis. So in effect, by performing this multiplication, what I've done is I've rotated this vector r. Another way of saying it is I've taken this unit vector, and the reason it's on the unit circle is if it weren't, then in addition to rotating the vector, I also would have scaled the resulting vector by changing its magnitude. So this was the idea that Hamilton was working on when he wanted to extend this concept to 3 dimensions. So he considered a complex number a plus bi, and ultimately realized he had to extend this not to 3 but to 4 dimensions, hence the name Quaternion. So if we call the Quaternion Q, we would then have to add Cj plus dk. And this is the form of a quaternion, where a is a scalar component, and then the remaining 3 components are imaginary or could be thought of as a vector. Now, if this idea of a scalar component plus a vector sounds familiar, having just considered Rodriguez's rotation formula, this is no accident. At this point, Rodriguez had all but invented quaternions, only he never quite called them that. And he didn't formalize it into an algebra like Hamilton did. But this idea of a rotation amount about a given axis has Rodriguez's idea all over it. Let's give this a number. We're up to 37. And Hamilton, it is said, wrestled with this idea of how to multiply so-called triples for years. And finally, one night, Hamilton had his eureka moment. This came on October 16th, 1843, while walking along the Royal Canal in Dublin. The key insight as to how to multiply triples of numbers led him to carving the defining equation into the stones of the Broom Bridge across which he was walking at the time. And these equations are as follows. He knew, of course, that I squared was equal to -1. We know this from complex analysis. But what occurred to him on that evening is that j squared is also equal to -1, and so is k squared. And all of these are equal to I times j times k, which is also equal to -1. And this is the equation that he carved into the bridge. Now, his carving has since faded, but today has been replaced by a plaque memorializing the equation. And for the last 35 years or so now, there's been an annual pilgrimage called the Hamilton Walk for scientists and mathematicians, where they retrace his walk in the remembrance of his discovery. So again, the idea behind quaternions is that it's a four-dimensional complex number. In fact, complex number algebra can be thought of as a subset of quaternion algebra. And again, we have a scalar part and we have a vector part. Now, quaternions in themselves don't merely describe rotations, much as the same way as complex analysis can be used for far more than just rotations. But handling 3D rotations is a very useful and convenient feature of quaternions. I should also mention at this point that the magnitude of a quaternion, much like the magnitude of a complex number or a vector, is equal to the square root of its components squared. Put a box around that and give it a number, 38. And quaternions really were inspired by the works of Euler, because of course everything was in those days, and also Cauchy and Rodriguez, as mentioned earlier. Now, this idea of the multiplication of triples can be summarized as follows. We consider the cyclic order, I, J, K, and in the order drawn, in this case in a clockwise direction, if we follow the arrows. And we can derive this as a result of this last part of the equation. If I multiplied both sides of this equation by K, then over here I would get a K squared, which is just minus 1. And over here on this side I would end up with minus K. And what that looks like is that I times J is just equal to K. If I go in the direction of the arrows, I times J equals K. Well, similarly, J times K equals I, J times K equals I, and you might have guessed it that K times I is equal to J. Now, what happens if we go in the reverse order? Well, then we get negative. So J times I is equal to negative K, because J times I, I'm going in the reverse order. K times J is equal to negative I, and of course I times K is equal to negative J. And an important feature to point out here with quaternions, unlike complex numbers, it's one of the things that makes these algebras different, is that multiplication of quaternions is not commutative. In the event where we multiply two complex numbers together, I can switch the order of multiplication and the product remains the same. Not so in the case of quaternions. Order in quaternions is important when it comes to multiplication. Not addition, however, but multiplication. We'll call these all number 39. And let's consider now the multiplication of two quaternions. We'll call one quaternion Q1, and a second quaternion we'll call Q2, 40 and 41. Multiplying these together produces something that is called the Hamilton product. Why? Because quaternion space is otherwise known as Hamilton space. So taking 40 and 41 and multiplying them gives us Q1 times Q2, and it is as follows. So notice we have a scalar part, and then we have an I, J, and K part to it. And we find each of these components just by multiplying the scalar parts of each of the quaternions. As a result, this calculation, the product, requires very little computational overhead. Unlike all the other methods we've presented up till now, these do not require any trig functions. And for those of you who are not aware, trig functions actually add a lot of computational overhead. They're relatively slow to perform. One of the real benefits of quaternions is that they process very, very quickly, and not surprisingly have found a home in 3D rotations of computer graphics, largely for the reason that computers, even the slowest computers, can process rotations this way very, very rapidly. Also, it doesn't require any matrix multiplication, which can also be a rather slow, tedious process. Equation 42 and a box around that. And let me also just mention at this time, for those of you who are like, what the hell just happened here? I'm really presenting you some of the results without going through all the math detail. But for those of you who are wondering how I came up with this equation, if I multiply Q1 and Q2, you do this just the way you would expect to do this, where I've got to multiply A1 times each of these components. And that's what gives me the A1A2, A1B2I, A1C2J, and A1D2K, for example. When I multiply the components containing I, J, and K, I would, for example, get a B1I and a B2I. This would give me B1, B2 times I, but I times I is minus 1. So that's where I get the minus B1, B2 from. On the other hand, if I multiply B1I times C2J, that would give me B1 times C2 times I times J. But we know I times J is K. So there's my B1 C2K. On the other hand, if I multiplied C1J by B2I, I would get C1 times B2, J times I, remember the order of those are important, J times I is minus K. So C1 B2 times minus K. Of course, the scalar parts, C1 B2, are commutative. I could have written this as B2 C1. But the imaginary or vector parts are not commutative, and those need to follow these rules here in equation 39. After this discovery, Hamilton spent most of the later portion of his life, in fact until his death, discovering and inventing Quaternion theory. He published several volumes on the topic, one in the 1840s, one in the 1850s, and another one shortly after his death in the 1860s. This last volume ran over 800 pages. So this truly is a vast topic, and we can't expect to do a real deep dive into it in the few minutes that I'm presenting it here. But I want to point out just the salient features of it, and enough so those of you who are interested in how it works can get some practical knowledge. And quaternions generally are not used very much in structural mechanics. They're used today in all sorts of other areas, which I'll present to you in a short while. But if any of you would like me to do a separate video where we deep dive into quaternions, then leave that in the comments below. And if enough of you express interest, then we can make a video on that. For a while after Hamilton's death in 1865, quaternions were a mandatory examination topic in Dublin. And then with the advancement of vector theory, quaternions fell by the wayside. But they re-emerged in the 1900s when they were found to be extremely useful both in computer graphics, as I mentioned before, but also attitude control of spacecraft, robotics, and even quantum theory. But more about that later. So let's consider how quaternions may be used to describe rotations in 3D. Consider a rotation of the form of an angle theta about an axis u. And to keep things even simpler, we'll assume that u is a unit vector that points along the axis of rotation. We know how to find unit vectors from any general vector. We just divide the vector by its magnitude. And this part is exactly along the lines of how Rodriguez parameterized rotations. It turns out to be a very intuitive way of thinking about rotations. It's just an angle about a certain direction. And Hamilton used the same idea. Now, we can form a quaternion as follows. We take the rotation angle theta and we write it in the form of cosine theta over 2 plus sine theta over 2 times the components of the unit vector in the I, j, and k directions. As far as why we use theta over 2 here and not theta, that requires quite a detailed explanation, and it's not something I want to cover in this video. If we do a deeper dive video, we can talk about it then. But the idea is that we've constructed this quaternion with a scalar part and then a vector part, which includes the I, j, and k imaginary or vector components, however you prefer to think of that. Equation 44. Then from before, we know that the general form of a quaternion is a plus bi plus cej plus dk, and by comparing these two equations, we can see that a is cosine theta over 2. So a itself is not the rotation angle, but it represents the rotation angle, as you can see by this relationship. Similarly, what happens here is that sine theta over 2 is scaling each of the components of the unit vector by the same amount. And the components of that scaled unit vector are b, c, and d. Okay, so this is a very clear way of how we take our rotation described here, convert it into a quaternion, and find our components a, b, c, and d. This is our rotation quaternion, and this quaternion happens to be normalized. Why? Because this is a unit vector, so that's normalized. And then if we square each of the components, we get cosine squared plus sine squared times 1. And we know that cosine squared plus sine squared is equal to 1. That's a well-known trig identity. Let's just make the point that this quaternion is normalized, much in the same way how in complex analysis we used a normalized rotation vector, or as we described it, a vector that lies on the unit circle. So we've done the same thing here, only instead of a unit circle, we're dealing with a unit sphere here. So we know as a result of this that a squared plus b squared plus c squared plus d squared is equal to 1. This gives us a magnitude of 1. I also want to introduce at this time the concept of a conjugate. We'll call that q star. And much in the same way how in complex analysis we would say a minus bi, we do the same thing here. The scalar part remains a, and the imaginary part, we flip the signs on each of the terms now. Minus bi, minus cj, minus dk. This is completely analogous to finding the complex conjugate. And let's just make a note here that this is the conjugate of Q. Number 45 and 6. The magnitude of Q can be found by taking the square root of Q times its conjugate. Why is that? Because if we multiply Q and Q conjugate, we get A times A, that's A squared. We get minus B squared here, but the multiplication of the i's give us a minus 1, so that's a plus B squared. Similarly, we get a plus C squared here and a plus D squared. So Q times Q conjugate is this A squared plus B squared plus C squared plus D squared. And of course, taking the square root gives us the magnitude. All right, so how do we use this rotation vector to rotate an arbitrary vector now in 3D? Well, let's define a vector. We'll call it V, and it has components Vx, Vy, and Vz. And what we do is we convert this vector now into a quaternion. Well, how do we do that? We just assume that the scalar part is 0. So V quaternion, I'll call it, is equal to 0 Vx, Vy, Vz. By just using the vector part in the vector part of the quaternion and a 0 in the scalar part, this is something called a pure quaternion. So a pure quaternion is something with a 0 scalar part. That's its definition. 47 and 48. Here's how simple it is to rotate a 3D vector using quaternions. V quaternion prime, I'll call it, the rotated quaternion, is simply equal to Q times V quaternion times Q conjugate. We know what Q and Q conjugate are from up above. We know what V quaternion is from here. And we know from before how to multiply two quaternions together. So we use that method of multiplying quaternions to first multiply the first two, and then take the result of that and multiply it by Q conjugate. Very simple and very quick mathematical operation. The result of that will give us the rotated quaternion in the form of a pure quaternion again, where I've called the component 0, Vx prime, Vy prime, and Vz prime, to indicate that these are the rotated values. Anytime that this is a pure quaternion, meaning a 0 scalar value, the result of this product will always yield a pure quaternion. So you will always get a 0 here. And then obviously with the results of that, we can find our rotated vector trivially by saying that our rotated vector, which will denote V prime, is just equal to the vector components of this rotated quaternion. So Vx prime, Vy prime, Vz prime. And that is it. That's how simple it is to perform a 3D rotation using quaternions. So again, we construct our quaternion this way. I remind you that it's a normalized quaternion. This vector, however, does not need to be normalized. Remember, in the case of our complex analysis, the rotation vector was normalized and lay on the unit circle, but the vector that we were rotating could be of arbitrary magnitude. Well, it's exactly the same way here. Q, our rotation quaternion, is on the unit sphere, so it's normalized. If for whatever reason it's not normalized, you could take the quaternion and divide it by its magnitude. But if you're using a unit vector here, then it by definition will be normalized. And then we just perform this multiplication. That's it. That's how simple it is to rotate a vector in 3D. Number 49 and 50 and 51. And a big red box around it because that's our final answer. Turning the page, let's talk about some of the advantages in using quaternions for 3D rotations. First of all, this method is immune to gimbal lock, which can be a problem when using Euler angles. Quaternions are also advantageous when it comes to combining rotations. And then something that's a very important point in the field of computer graphics is something called spherical linear interpolation. For those of you who use 3D packages such as Blender or Maya, or Unity or the Unreal Engine, for example, all of these by default use Euler angles, but under the hood you can use quaternions too to describe rotations. And the idea is that with these tools, what often happens is one uses keyframes, and at these keyframes you would set the orientation of a 3D object, and then leave it to the software to interpolate between the keyframes. A commonly reported problem is that when you do this using Euler angles, it provides some really weird and inconsistent interpolations. There are any number of videos on YouTube that talk about this. So spherical linear interpolation is a technique used for smoothing the interpolation between two orientations in 3D space. It's particularly important in computer graphics and in robotics. And the idea is that while linear interpolation moves in a straight line between these 2 points, SLERP moves along the surface of a sphere, which is crucial for rotations because it maintains a constant angular velocity, and it produces the shortest path along the sphere's surface. Another advantage of quaternions is the compact representation that they provide, and as we mentioned earlier, they're very computationally efficient. Even since the 1950s and using computers with minimal processing power, it was found that using quaternions could produce very smooth 3D rotations. So that brings us to the uses of quaternions. We mentioned already computer graphics and robotics in the context of using SLERP, but they're also used in aerospace engineering for attitude control of spacecraft. They're used in virtual reality, and also, believe it or not, quaternions have found a home in quantum theory. And for all of these reasons and more, quaternion theory, which had all but fallen by the wayside in the late 1800s, found a revival in the mid-1900s and beyond. And any of you that use an iPhone, for example, iPhones use quaternions for device orientation tracking through their motion sensors. The core motion framework in iOS uses quaternions to represent 3D rotations smoothly and avoid gimbal lock issues. So just about all of you, whether you realize it or not, are making use of quaternions every day. And with that, we've come to the end of this video. And not just the end of the video, but the end of this mini-series. But before we go, and as I've promised, I'm going to go all the way back to the beginning of part 1 and do a comprehensive review of all 4 parts, where I will summarize and compare the various methods that we've talked about in parts 1 through 4. Okay, so starting at the beginning. We first started with the Euler angle method, and we talked about the fact that Euler angles involved 3 successive rotations about 3 different axes. By multiplying these rotations together, we got an overall transformation for the full 3D rotation. We talked about how the rotation sequence is important when it comes to Euler angles, and once we define a rotation sequence, we need to stick to that rotation sequence throughout the modeling process. We ended up with a rotation sequence that looked something like this, which involved matrix multiplication and a lot of trig functions. The advantages of using Euler angles include that they're simple to understand and very intuitive rotations in terms of roll, pitch, and yaw. They're very good for user interfaces, for manual input or interpretation of rotations, such as in CAD software or flight simulators, but they tend to be relatively slow to calculate. And of course, for large rotations, we run the risk of the possible gimbal lock condition, where we lose a degree of freedom. We also, along the way, spoke very briefly about the difference between instant rotation rates versus Euler angles, or really Euler angle rates, and how these are actually measured about different axes. Then we considered direction cosine matrices. Direction cosine matrices have the advantage of being very high precision and give you an explicit representation of rotations, especially in the case of complex or chain transformations. They're very good for applications like inertial navigation or orbital mechanics, where explicit transformation matrices simplify coordinate changes. So they are suitable for high precision and long duration computations, and they're also directly usable in systems that require matrix operations. The downside of direction cosine matrices are that they come with a high computational cost and a large storage requirement because you're storing 9 different parameters. Then we took a look at the Rodriguez rotation formula. They're very efficient for a single known axis and angle. They compute very quickly. They require minimal parameters for representation. It's just a vector and a rotation angle. And it avoids the complexity of matrices and quaternions in simpler cases. Its weaknesses include that they're not suitable for general or complex 3D rotations. And then that brought us to the topic of quaternions. Quaternions are best for efficient, smooth, precise rotation in 3D applications. It avoids gimbal lock like we see in the Euler angle method. And really the big plus in the case of quaternions is the compact storage and reduced computational cost. The weakness with quaternions is that they tend to be harder to visualize and to interpret. And that brings us to the end of this video. I hope you found something useful in it somewhere. If you did, and you'd like to support more of this content, please go ahead and hit those like buttons below. This really helps with the YouTube algorithm. Or better still, click the subscribe button and the bell icon so that you can be notified of any future video releases. If you have any questions, comments, criticisms, or found my video just plain boring, I'd like to hear from you in the comment section below. As always, you can download a copy of these lecture notes from the link in the video description. Thank you very much for watching, and I will catch up with you in the next one.